Chris's point is what we know, because it's been used so much, is that the mercuric chloride pretty well always works. Not absolutely. I've had batches of reference material where I'm certain the mercuric chloride was in there because I could analyze it and measure the amount of mercury, and it was there. But the CO2 concentrations changed with time. There are some organisms that are sufficiently mercury tolerant, and if your sample gets contaminated with that, then you're doomed. The other problem is that mercury attracts a certain amount of attention as a hazardous material. Chris was alluding, if it's basically below 0.04%, it's not considered a hazardous material by the US Department of Transport for shipping it. That doesn't mean the person who receives it doesn't perceive it as a hazardous material, and probably shouldn't. I've had two interesting cases over the years. Once, they'd left some bottles with mercury chloride on the deck of a ship. It froze, the bottles broke. They picked up the box, now containing water, tipped it up against the water, flowed out down their clothes. They went, what's in this? And somebody said, oh, it's just seawater with, and they said, well, yeah, that's fine. With some mercury. Oh my God, I'm gonna die. And they were sick that night. This was in Germany, where industrial accidents are even more strongly reportable than they are here. And I had extensive correspondence reassuring people that according to medical people that I could consult here, skin soaked in this, subsequently washed off, was not a hazard at those levels of mercury. But another person was mouth protecting material, and they swallowed some. So I had long telephone calls with the Hawaii poison control officer explaining what exactly they had swallowed and suggesting in actual fact it was probably the seawater that was going to do them more harm. But it was kind of a trade-off there. And so they watched that person and took hair samples over a protracted period after that to see whether the mercury was being eliminated as they expected. It's potentially hazardous. If you have a great way of killing things without using something that's noxious, we'd love to know. But somehow there's a mismatch there. Also, it's got to be something that doesn't upset the CO2 system. And a lot of poisons actually have an acid-base property to them. And that's a difference. Also, it's got to do it pretty damn quick, because you don't want to know what this sample would have been like 4 hours later. You want it right now as you killed it. And mercury seems to do this, and we haven't yet found something that does it better. But to be fair, we haven't looked very much either. This works so well, we've gotten on with other details of our lives.
But we have, it took us years and years to get it, but we have an official certificate from the Department of Transportation now that says at the levels that we poison, that these can be shipped as not hazardous, just as seawater samples. And we can provide those to people if you want them. I don't know that I want to put it on a website, but
if you were to search for it, you will actually find it deep in the bowels of the Department of Transport website. That's how I first found it, via Google, and then I learned how it got there.
I think where we run into trouble though is stuff like chips off on the ramp crews and stuff, because there they have to take a concentrated mercuric chloride in a small frac, and they're stealing up into these marine protection
Right.
areas. And the concern is that in rough seas or something, if that bottle flips off onto a protected marine system, now is this a concern? I've rationalized that the
Yes, is it a large concern? Some days, perhaps. But the piece that I would say about the hazard of this, the real hazard of this, is making up that concentrated solution in the first place. Let me just emphasize this. You're using then powdered mercuric chloride. And powdered mercuric chloride is a clear respiration hazard. It's fine dust. If you breathe it in, it's almost certainly not good for you.
Sarah took care of that for you, so.
When we're at the
None of you have to.
saturated solution, it's about 7 grams of mercuric chloride, 7.5 already meaningfully dilute. Once you then throw it into an ocean and drive your motor over it a couple of times, it's probably well stirred and down at levels that probably aren't worrying anybody. But you're right, it went through a point where it was potentially really quite noxious.
Well, I mean, I
And
don't
the
know.
paperwork
Has
would be
there been any
horrible.
formal inquiries when, like, I thought there was an
Well,
issue with the North.
Yeah, there has been, but we got around it by.
Do you think we have time, or maybe just? Yeah.
5 minutes, 10 minutes.
Oh, well, 5, or we can just go there. I need to warm up.
This amount in a 10
2
by 10
bucketfuls or whatever,
square
yeah.
meter thing of water, that it would be so dilute that it would be a non-issue, and then they bought it, so it was fine.
Okay, I hate to do this, but we're gonna have to hold the questions on this for another point. We can maybe discuss
Bear in mind,
this
you'll be doing a sampling thing this
You're
afternoon.
during
I'll be
the
hanging
sampling.
around.
We
I'll
can
see
talk
you all.
about this some more, and then any questions that sort of apply to the whole group, you know, rather than specific circumstances, maybe we can address later. But right now, Alec Wong, who is here over at Woods Hole Oceanographic, is going to be talking briefly about determining PCO2 with an underway system. We'll also be seeing this as part of the afternoon activities. So he's going to give a brief introduction, and then we're going to split up into our lab groups for the afternoon's activities. Take it away, Alec.
All right, thank you. So I guess Chris is going to later show how to collect samples and do a demonstration. And I'm going to show a demonstration for sampling of pH, which doesn't involve, I mean, for my method, I don't use the mercury chloride. I just sample it and then put it in the measurement right away. So, but you got to have the capability of doing that quickly after sampling. After several hours, the pH is going to change if you don't kill it. So that's the issue. And this is talking about the PCO2. I'm sorry about it. And this is just give you a brief idea of how do we measure PCO2 in a stream of seawater. So most of the time, people using this method to measure underway, to measure CO2 in the underway mode. So basically, you have seawater pumping into on board and into some pipe, and then go to the wet lab. I'll say most of the time, and then in the wet lab, you set up this infrared-based method, and then you take measurement of CO2 gas samples. And this is probably the most mature, I would say, PCO2 measurement. It's been a while for a long time. And there are people also, there are a group of people using this method to measure PCO2 in discrete mode. That is, you collect some samples, for example, 500 mils of seawater, discrete samples, and then using some known headspace of air to equilibrate your discrete sample with that headspace of air, and then you can measure that PCO2 in the bottle. And this method is, there's no constraint on the seawater. So you can continue flow your seawater through the system, and then using the NDIR infrared, non-dispersible infrared analyzer. Most of the time, people using LICOR models to measure it. One of the key thing you have to know is that in this method, you only measure gas-phase samples. So that means somehow you have to convert a liquid sample to a gas-phase sample, and then using this method to measure the equilibrated gas sample. And then definitely you need, besides the infrared analyzer, you're going to need some kind of equilibration mechanism. And there's at least 3 basic types. And then in my lab, later on in the lab, you're going to see this is the first type. It's most common used type. In that you have some kind of cylindrical structure, and then you have shower head on the top of it. And then there's a head space. The seawater, you're going to sprinkle down in a container, and then equilibrate with head space air in terms of the CO2. And then you withdraw some of the equivalent CO2 to the IR analyzer, and then you can measure the CO2 concentration. There's other types, like the bubbling type of analyzer, equilibrator here. That is, you have certain kind of your certain carrier gas, and then you bubble your seawater through the equilibrator, and then using the carrier gas, and then the CO2 in the seawater are going to equilibrate with that carrier gas, and then at the end you measure the carrier gas. And
on Thursday, my board system is a bubble equilibrium.
Yep. So, and the third type is I saw a few people using this type of mechanism, which you have certain film. This film is permeable to CO2 gas and also permeable to some other gas, because this just depends on the size of those holes on the film. So your CO2 gas phase into the liquid, into the IR analyzer to measure CO2 concentration. And then all of those, most of the analysis, unless you want to do some quick setup and then do this, most of the system we have are either commercialized or built yourself. You need to have some kind of calibration procedure. And calibration, basically we use some standard CO2 gas to calibrate the system. One of the, I think I wouldn't say it's drawback, but for the IR analyzer, you have to calibrate the system frequently so that to maintain. There will be some drift if you don't calibrate necessary. And then you have to compensate the drift of the IR analyzer. And that's at the beginning of the measurement, you always do a calibration, and after some time you do another measurement, you have to calibrate again. In between, just depends how frequent you measure the samples, and probably an hour is okay. You can take several measurements before you take another calibration. And then most of the most of the analytic system will need some type of engineering effort to make the system automatic. That's actually, I would think, is the most challenging part of this method. I mean, the methodology is simple enough, but to make it work in an automatic way is challenging. And then especially the precision we're talking about here is 1 microatmosphere CO2. But if you do this correctly, you can measure better. But that's going to need a lot of engineering.
Alex?
Yeah.
I came across a different way to equilibrate. People from the University of Liège, they are using glass beads, and the water flows along the glass beads.
Yeah, I would think falling into the first type, because I use that too.
In estuaries, it's quite convenient because there is so much particulate material.
The surface area and increase the surface area. So, yes. And I kind of allow you to the first type. This, and this is the some kind of basics of for this type of method. This is the infrared spectrum of CO2 and water vapor. And if you look at the wavelength microns, it's about at 4 or 3, there's a peak of absorbance for the CO2, and that's some kind of overlap with the water vapor. And then so in a real environment, in a real measurement, we have to consider that when you do the CO2 measurement, because you either remove the water vapor or you correct it. So people have been doing that both ways. You can remove the water vapor so that the water vapor won't connected to two of the detectors. One is water vapor, and the other one is CO2. Before that, you have to have some kind of filters to filter the wavelengths you need. I guess that's one more. So this is by Cosier 2000, and then they did a very nice comparison of all kinds of equilibration, underway CO2 system using different type of equilibrator for during a cruise, and everyone measure the same water, and then compare the result to see whether there's whether they agree or there's a significant difference of a different type of equilibrator. As you can see from the top, there's a total volume of each type of equilibrator would need to measure the CO2 concentration. And then you see, you can see in the middle, and then some people measure wet gas content, and most of them measure dry CO2 content. And then the time to reach equilibrium varies, and I haven't figured out them myself, but I think if you have a very long time to equilibrate, that means you have a very long time to actually average the measurement you have. And if the equilibrium time is sufficiently short, you actually have instantaneous kind of measurement, which I think you do need that faster response. So that's basically what this happens. And this is you're going to see in the lab, and this is kind of a two-stage equilibrator, shower head type, and then there's a reverse cup inside, and then kind of seal off the head space. And then the second equilibrator basically provide, because once you withdraw some air from this cup, you're going to create some kind of negative pressure. To compensate that withdrawn air, you can have a second equilibrator to supply pre-equilibrate CO2 air sample to this, and then so that maintain the pressure in there. And this is the old version of, I think I can skip this, and then you're gonna see this in the lab. So I'll stop here and.
Okay, thanks. And yeah, we'll be seeing his setup in the flesh or in the metal or whatever you want to call it later on this afternoon.
All right.
Yeah, Andrew.
Alan, perhaps while you still with that picture, you'll emphasize just how important temperature measurement is to this.
Right. The temperature will affect two things, or more than two things, I guess. The main thing is CO2 is very sensitive, as Andrew pointed out. PCO2 is very sensitive to temperature. So you need to know exactly what temperature you measured your sample, and then you can either correct to whatever the temperature you desire. And this system have a built-in sensor. This is actually a temperature meter, and then this temperature probe into the main unit of the equilibrator. So it's matter exactly what gas, what temperature inside the equilibrator, and then that will tell you the. It's not the measurement temperature, but it's close to the measurement temperature, I would say. The real in situ temperature will be different from this because there will take time for the seawater to actually flow through this equilibrator. There are some temperature difference between this and the real intake seawater. So you have to actually convert that temperature difference from this measurement to actually the in situ PCO2 measurement. So go ahead.
Just to add a little bit, Alec mentioned that with this system working well, you have a hope certainly of a precision of the order of 1 microatmosphere, which is about 1 part in, let's say, 400, a quarter of a percent. If you had the temperature change by 1 degree centigrade, that's 4.25% difference. So you have to have that, to get that 1/4%, you need the temperature, therefore, 1/17 of a degree or better. So
Yeah.
0.05 degrees centigrade is the level you should be hoping for temperature measurements to make it work as well as it can work. Clearly, this is potentially problematic for many setups and thinking about it, but this is a difficulty with CO2. The temperature change for this PCO2, for the air-water equilibrium, is this change that if you just take the water and you warm it up 1 degree, the PCO2 is going to increase by about 4.25%.
Yep. For this type of system, if you install on a larger ship, from the intake to actually the wet lab, it's going to be several hundred, right? Several hundred yard, if I remember, or feet long. And then the, I don't know exactly how long, but the temperature offset between the intake and this, probably a 0.5. Okay, I've seen it 0.5, 0.2, 0.3. So if it's 4% of 1 degree, and then the other will be 2%. If it's 2%, it's already out of the precision we're talking about here.
So you had to have a good thermometer. In fact, for that, you had to have 2 good thermometers because you wanted to do the adjustment between them.
Yeah. And another kind of issue is that for the light core itself, inside the cell, again, it's also temperature dependent. So you have to know exactly inside of the light core analyzer.
Okay, on that note, I'm going to have to cut it off, and I'm going to have to say we're going to have to discuss temperature issues on site while we're looking at it. Group A will be going upstairs to experience sampling.
Yeah.
Group